What if you could build an entire operating system around a single, unchangeable constitution, a master plan that lays down every single rule for every program and then gets enforced with the raw power of the CPU itself? Well, that's exactly what we're going to dive into today.
Okay, so let's kick things off with the central puzzle this whole system has to solve. Just imagine every single app on your computer and the operating system kernel itself all living in one giant shared space and memory. How on earth do you stop your browser from accidentally scribbling all over your text editor's data? Or even worse, a critical part of the OS? This is the whole idea behind a single address space operating system, or a SASOS. See, your typical OS gives every app its own little private sandbox of memory. But a SASOS throws everyone, and I mean everyone, into the same giant swimming pool. Now, this is fantastic for efficiency, but it's a potential nightmare for safety. So how do you keep them from splashing all over each other?
Well, the answer isn't to just cross your fingers and hope everyone writes perfect software. No, the real solution is to create a set of unbreakable rules, a master plan, and then use the CPU's own built-in features to enforce them. This changes security from being a suggestion into a physical law of the system. And that master plan, it has a name, the IPCKU MAP. This single document is the blueprint we're going to explore. Think of it as the single source of truth that defines both how programs are kept apart and exactly how they're allowed to talk to each other. It really is the system's constitution, all written down.
And what's so smart about this map is how it splits this huge problem into two clean halves. First, you've got isolation. It draws these strict, hardware-enforced lines in that shared memory pool. And second, communication. It lays out standardized, safe pathways for programs to talk across those lines. So let's break down that isolation part first. The map gets this isolation done by creating something called hardware-locked domains. So if that shared memory is one giant building, this part of the map gives each critical system service its own locked room, and the CPU itself is the only one holding the keys. The tech that makes all this possible is called Intel Protection Keys, or PKU. It's a feature baked right into modern CPUs. Basically, the OS can paint every page of memory with a key, a number from 0 to 15. A program can only touch that memory if it currently holds the matching key in a special CPU register. If it doesn't have the right key, sorry, the hardware itself just says nope and blocks the access. No software check required.
Now, this is where it gets really cool. Look at how directly the map turns this hardware feature into the system's architecture. It's a dead simple one-to-one mapping. Protection domain 1 gets hardware key 1, and that is assigned exclusively to the sex display server. Protection domain 5 gets key 5, and that belongs to the sex drive server. There's no ambiguity here. It's a rigid, predictable layout where nothing is left to chance.
So here's the bottom line. When the storage server needs to run, the CPU gives it key number 5. That key unlocks all the memory tagged for the storage system. But if that server ever, for any reason, tries to touch a piece of memory tagged with key number 1, which belongs to the display server, the CPU itself stops it dead in its tracks. Bam! A hardware fault, not a software error. That's how you get rock-solid isolation even when everyone's technically in the same room.
Okay, so we've locked every critical service into its own secure room. Awesome. But they still need to work together, right? How does the desktop shell tell the display server, hey, draw a window for me? That brings us to the second half of our blueprint, the communication system. The solution is basically a universal switchboard, a system-wide phone book. Instead of programs having to guess or hunt around to find where other services are, the map defines a standardized list of addresses. It calls them well-known slots. And here's exactly how it works. The map dictates, forever, that if you want to talk to the storage server, you send your message to slot 1. Need the display server? That's always at slot 5. It's a permanent, system-wide directory. And look, the map even specifies the language each server speaks, listing the exact commands they understand.
All right, let's put all the pieces together. We've got our hardware-enforced rooms, and we have our universal phone book. Let's trace a simple, real-world request to see how these two systems work together beautifully.
So here's our scenario. The Silk Shell process, which handles the user interface, needs to tell the sex display server, which handles the screen, to create a brand new window.
And this isn't just some theoretical document sitting on a shelf. The map is wired directly into the system's code. So a developer working on the shell doesn't have to remember some magic number. They just use a nice, clear constant, slot display, and the map is what defines that constant as being slot number 5.
So the process is just dead simple. The shell knows it needs to talk to the display server.
It uses that constant from the code, SLOT display, which tells it the address is slot 5. All that's left is to figure out what to put in the message.
Okay, back to our routing table. Silk Shell looks up slot 5, and it confirms, yep, that's the endpoint for sex display. So it knows exactly where to send the message. But the map gives us another huge clue. It lists the types of messages sex display is expecting, including one for, you guessed it, creating a window.
So, what's the exact command for creating a window? The IPC map points us in the right direction with that code, 0xDE. But to get the full story, we just have to cross-reference it with the server zone official manual. And boom, here it is, pulled straight from the sex display server's documentation. The command pdx-sex window create has the value 0xDE. This is the exact word, the specific opcode that the display server understands means create a new window.
And that's it. The Silk Shell process packs up a message with the command 0xD and sends it off to slot 5. The kernel routes it to the sex display server, which gets the message, understands the command, and draws the window. The entire elegant interaction was governed, secured, and made possible by that one master blueprint.
So, let's zoom out for a second. Why is this whole architectural approach so powerful? What's the big deal about having this kind of master plan?
Well, there are 3 huge takeaways here. First, security is baked in from the very foundation. It's the CPU hardware enforcing the rules, which is way more robust than any software check. Second, communication is completely predictable. There's zero guesswork. Every program knows exactly where to find every core service. And finally, you have a single source of truth. This one file is the definitive guide for the system's entire security and messaging architecture. At the end of the day, the IPCKU_map is so much more than a config file. It's an architectural constitution for the entire operating system. It's written in a simple text file that you or I could read, but its rules are enforced with the absolute unquestionable authority of the CPU silicon. And that leads us with a really fascinating question to ponder. If the hardware itself is enforcing the most fundamental rules of your system, how much simpler can your software become? How much defensive, complex code can you just get rid of because you know the foundation isn't a suggestion anymore, it's a physical law?